now we are going to start with an important topic, that is the hybridization, right. See, what is the hybridization? It is actually intermixing of atomic orbitals. It is intermixing of atomic orbitals. What atomic orbitals? Those atomic orbitals which have slight difference in their energies. Like for example, we have these kind of orbitals arranged, right. So that means they can intermix their energies, they can intermix their energy. So that means it is applicable only to the orbitals which have slightly same energy, right. So that means intermixing of atomic orbitals of slightly different energy, and when they just mix up, they give rise to the new orbitals which are called as hybrid orbitals, and they have same energy and same shape. Right. So that means when they just intermix, they give rise to new set of orbitals named as hybrid orbitals, equivalent in shape and equivalent in energy. This is what is the hybridization. But now when we perform hybridization, there are certain rules which is to be followed, right. See, number of hybrid orbitals will be always equal to the number of atomic orbitals that get mixed up. Suppose I say that 2s and 2p are going to intermix their energy, so that means how many orbitals are there? S has one orbital, you know that, and the p has 3 orbitals. So that means 4 orbitals are going to mix up. So when these 4 orbitals are going to mix up, they will give rise to 4 hybrid orbitals, right. And hybrid orbitals will always have same energy and shape. It is clear from the definition as well, that as I told you, that after intermixing they will give rise to the orbitals which will have same energy and same shape, right. They are more capable of forming stable bonds. They are capable of forming more stable bond as we compare with their atomic orbital. And they will direct themselves in the space in such a direction in order to minimize the repulsion, so that they can have a perfect geometry, right. So as we will be discussing that, see, as you can see the geometry of these molecules, so they are oriented in space in a preferred direction so as to reduce the repulsion and give rise to a perfect geometry or stable arrangement. And moreover, you have to know that only valence shell electrons are going to participate in, only valence shell electrons are going to participate, and excitation is not a compulsory factor. I will just explain you with an example, then these will be clear, right. And which atoms hybridize more? It is C, O and N, and the terminal H, Cl and F, they do not hybridize much, right. So let us take an example, then it will be clear. See, suppose I have an example of CH4. I am going to show you the hybridization of carbon in this case. So in this case, which is my central atom? Obviously C, right. So I am just going to write the atomic number for it. So it is 6. Now I will write the configuration: 1s2, 2s2, 2p2. I am just going to draw the orbitals in order to show that how the electrons are present. So we have this 1s, we have this 2s, and we have this 2p. So likewise, these are present. So that is a ground state configuration. We say that this is a ground state configuration. Now I am going to excite it, right. So when we excite it, we know that inner shells do not participate. Only those orbitals which have same energy participate. So that means in this 2s and 2p is going to participate. So this is what originally we have, right. So now what I am going to do, when I am going to supply energy, this electron is going to be moved from here to this empty orbital, right. So in this way, this is an excited state. So in this way, now 4 half-filled orbitals are there, right. So they have to accommodate 4 hydrogen. So they will accommodate 4 hydrogen because they have 4 unpaired electrons. So this is our hybridization. So how many s participated? Obviously 1 s orbital participated. How many p participated? Obviously 3. So its hybridization becomes sp3. So this is how you are going to give the hybridization of this thing. And you know, there is one more method, like if I give you some formula, suppose I give you NH3 and I ask you that I just want predict the hybridization without doing this process. So you have a clear cut formula where you can just predict the hybridization. How? See, as we know that there is a formula that is the half into valence shell electron of central atom plus number of neighboring atoms minus if there is a charge of cation and plus if there is any charge, if it is in an ion, right. So here I am going to find the hybridization for NH3 by this direct formula. So that means it is half, the central atom is obviously N, and what valence electron does it have? You know that atomic number is 7 and valence electron is 5. So it is 5 plus how many neighboring atoms? H3, that means 3. And do you get to see any charge above? No. So that means we are not going to follow this rule because it is neither cation nor anion, it is a neutral molecule. So that means it is 1/2 into 8 comes out to be 4. Now I am going to distribute this 4 among S, P, D, right, number depending upon the orbitals. So S has 1 orbital, so it will be S. P has 3 orbitals, so 3. We have finished with 4, so again its hybridization is sp3. So this is the formula to predict the hybridization. When you have to predict the hybridization directly by not performing this task, then you can just predict by using this formula, that is half into valence electron of central atom plus number of neighboring atom minus if it is a cation, charge of cation, and plus if it is an anion. So likewise we can have different hybridization. See, we can have sp hybridization, we can have sp2 hybridization, we can have sp3, sp3d, sp3d2 and sp3d3. There can be more hybridization also, but at your level you should be familiar with these hybridization. So when I talk about sp hybridization, so that means it is intermixing of 1s and 1p. Right, and you know what is the shape is going to be? See, it is 1 and 2 orbitals, so it will give rise to a linear geometry this way, right. And likewise sp2, 1s and 2p, the total of 3, so that means they will give rise to a trigonal geometry like this. And this sp3 is 1s and 3p, it will give rise to a, or total is 4, it will give rise to a tetrahedral geometry. sp3d, that is 1s, 3p, 1d, it is give rise to a triangle bipyramidal geometry. And sp3d2, 1s, 3p, 2d, this is what you can see here. So total of 3, 4, 5, 6, it will give rise to an octahedral geometry. So this is how we predict geometry in these cases. I will write one example for all. sp hybridization, let us say BeCl2, sp2, let it be BCl3, boron trichloride, sp3 let it be CH4, sp3d, so it's total of 5, so let it be PCl3, and sp3d2 is 3, 4, 5, 6, so it comes out to be SF6, sorry, it is PCl5. So likewise, and sp3d3 is IF7. So like this way we can have a different formulas. What you have to do, you have to pick the central atom, write its ground state configuration, do the excitation if it's possible, and if there is no excitation required, then it is not a compulsory factor that always you have to show the excitation, right, and then just combine them with the half filled orbitals. So this is how we are going to perform the hybridization, right.